Okie dokie. Hey, Biochem. This is the second day of electron transport chain. After we do this, we'll do ATP synthase, and the combination of the two, electron transport chain and ATP synthase, is considered oxidative phosphorylation. Oxidative for the electron transport chain part, and phosphorylation because we're going to phosphorylate an ADP. Okay. Oh no, I paused it. Okay. After watching this video, you should be able to calculate the delta G for moving electrons. Calculate the delta G for coupling electrons moving through the ETC with pumping protons. Recognize the three types of hemes. We went over this last time, but I'm just going to bring it back up again because they go with chemical asphyxiation. And then we'll do the malate-aspartate shuttle. Okay, so what happened last time is that we went through the electron transport chain, going through all the different electron acceptor molecules or ions. And the reason why we do this, and we do it with the math, is so that you know the why. Why is it that electrons flow from NADH or FADH2 all the way to oxygen, okay? And the reason for that is that oxygen has a much higher or more positive reduction potential. And this is exactly why we breathe oxygen. We don't breathe water. We don't breathe CO2. We breathe oxygen because it loves electrons so much. It's such a great final electron acceptor. If an organism doesn't use O2 as its terminal electron acceptor, then it's considered anaerobic. The reason that we're considered an aerobic organism is because we use oxygen as the final electron acceptor of the electron transport chain. And there's no possible way for the electron transport chain to run in reverse. That it wouldn't be favorable. We wouldn't be able to pump protons. It has to go in the direction that it does from NADH, complex 1, complex 3, complex 4. FADH2 comes up through complex 2, and then 3, and then 4, because every electron acceptor down the chain has a higher reduction potential than the one before it. Again, it's like pass the baton. The person that you're passing the baton in front of you wants it more than you want it. Okay, so this is a figure that I like a lot because it shows all the things without having way too much detail. But it shows starting with NADH, electrons getting passed up to Q, which reduces to QH2, which then donates protons to complex 3. They go to cytochrome C, the mobile electron carrier in the inner membrane space. And then C drops off protons to complex 4, which is where oxygen gets reduced to hydrogen. And then we can also start here at complex 2. Succinate to fumarate is oxidized, passed to FADH2, passed to Q, to 3, to 4, so on and so forth. This whole flow here of moving of the electrons has a large negative delta G. We've calculated that. At each complex, the delta G is negative, which means that that energy is used to move protons against their concentration gradient and against their electrogradient. And so you can see that the inner membrane side of the matrix of the mitochondria is a positive charge. When you move a positive ion to a positive side of the membrane, that is unfavorable. When you move a molecule against its gradient, that is also unfavorable. And the energy to do this comes from moving the electrons. So the reduction potential in the electron transport chain, using the reduction potential, we can move protons into the inner membrane space. What this creates is a concentration imbalance. A high concentration of protons in the inner membrane space and a low concentration of protons in the matrix. It also creates an imbalance of charge. across the membrane. More protons in the inner membrane space make that side of the membrane more positive. So we have what's called the proton motive force. How many different colors can I use? It's also called the chemiosmotic potential, or chemical electropotential. Okay, and eventually we're going to use this energy to make ATP. Okay, so protons are going to come back down their gradient to the negative side of the membrane. That's going to release energy and give us ATP, but we're not there yet. We're at the place where moving the electrons through the electron transport chain, that's this, is favorable, and the energy released from that is used to pump protons. Okay, so we're going to do a math example because I think it's going to be really important that you're able to prove this to yourself, that these two things do couple together. So I suggest that you get out a calculator. I've given you almost all the information that you need. Anytime that you do an assignment, I'll always give you a reduction potential table. You just need to know how to use it. Okay, so the question of this is, what is the maximum number of protons that can be pumped through complex 1? Assume temperature is 300 Kelvin, membrane potential is here, pH of the inner membrane space is 6, and pH of the matrix is 8, and then I've got some equations here. Okay, so I always start with what is overall going on here. So this is a coupling thing, so I'm going to couple the delta G, and I'm just going to put of redox through complex 1. I'm going to couple that, which means add to, the delta G of transporting a proton. And I want to know the maximum number, so that's going to be this value. And that means that I'm going to set this less than 0. Okay, you could set it equal to 0, it doesn't matter to me. But we can only have one variable to solve for. Okay, so let's start, we'll go left to right here. We'll start with the redox. And in complex 1, we start with NADH dropping off electrons to NAD+. NADH dropping off electrons to complex 1, which oxidizes to NAD+. So then I go to my table and I see, okay, here's my half reaction. I need to flip this one, and I need to make sure that I've got all the pieces there. So plus H+, plus 2 electrons. Scooch this over. And then because I flipped this half reaction, I'm going to flip the sign on this. So this is going to be a positive 0.320 volts. And through complex 1, when complex 1 is done passing, it finally passes to a ubiquinone. So I know that we are going to pass to a Q, and that will make a QH2. Okay, and that's this equation right here. Q is also called ubiquinone. And I just need to finish this here. There's two of those. And now I didn't change anything there, so I can leave this as plus 0.045 volts. And then I add the half reactions together. Before I do that, I make sure that I cancel anything out that's the same on both sides. Goodbye, goodbye, not you, not you. And then I add them together and get NADH plus Q plus a proton goes to NAD plus QH2. And then my delta E here is these two added together. 0.365 volts. All right. And then I have an equation up here that has the delta E in it. So delta G for this, N is the number of the number of electrons, that's 2. And F is Faraday's, 96500 joules, mole, volt. And our delta E, we just calculated, is the change in reduction potentials, volts. And if I calculate this out like I did previously, I get a really big negative number, which always makes me happy. Negative 70,445 joules per mole. Okay, and this makes sense to me because Q has a higher reduction potential than NAD, and therefore if we pass from NADH to Q, we should have a favorable passing of electrons, which we do, and of course favorable means negative. Okay, so I now have this number is going to go in here, and now I need to do my delta G of transport. And I guess I'll just slide over and do it to the side. Okay, so if you remember, if we've got our mitochondria, it has two membranes. Our electron transport chain sits on the inner membrane. Okay, and it says that the pH of the inner membrane space was 6, and if you do the anti-log of this, so remember pH equals negative log of H plus concentration, you'll get 10 to the minus 6 molar. And then of the matrix, we had pH equaled 8, and again that's 10 to the minus 8 molar. Now, we are moving electrons from the matrix to the intermembrane space. That's just something you need to know about the electron transport chain, which makes this C2 and this C1. And you also need to know that this is the positive side of the membrane and this is the negative side of the membrane because we have a charge imbalance and we have an electric imbalance. Okay, so what that means is, let's go red. Delta G of transport of one proton is, again, you have the equation off to the side, 8.315 joules mole Kelvin. I gave you the temperature as 300 Kelvin, and then it's natural log over C2 over C1, so 10 to the minus 6 molar over 10 to the minus 8, and then we're going to add that to the second part. The charge of a proton is +1. Again, we have Faraday's, 96500 joules moles volts, and then my proton has a plus charge, and it's moving to the plus side of the membrane, so that's unfavorable. So this whole thing will have to be positive. So I'm going to keep this as a positive value, 0.05 volts. Okay, do your math, have fun. I got a positive 16312.59 joules per mole. Does that make sense? Yes, because I'm moving things against their concentration gradient. So this entire unit up here should be positive. I'm moving it onto a favorable side charge of the membrane, so this should also be positive. So that makes sense to me that I would get a positive value. Okay, now comes the fun part. Put them together. So I have, again, the magical equation is this one. So I've got negative 70,445 joules per mole plus X is the number of protons that are going to be moved, 16,312.59 joules per mole. So it has to be less than 0. Do your math. Move the negative 70,000 over, divide by 16,000, and what I get is 4.318 protons, and you can't have 0.318 of a proton, and we round down because we don't create mass here, and we can move 4 protons through complex 1 per a single NADH, which is exactly what we went over, is that complex 1 pumps 4 protons. Okay, so again, what I'm trying to do here is give you a mathematical justification for the energy that is released by pumping protons, is released by moving electrons, is harnessed to pump a proton, or pump many protons. And the whole goal here is to create that chemiosmotic potential. So I would say goal of ETC is to create, maybe we'll just do electrochemical gradient. Okay, so again, electro means we have a charge separation across the membrane, and chemical means we have a concentration difference across the membrane, and this can be harnessed to make ATP eventually. No, you can't write from right to left. Nobody would know what's happening. Harnessed to make ATP, but that's later. The electron transport chain itself makes no ATP. It just moves electrons and pumps protons. That's it. All right, so moving on just a little bit, I want to come back to this idea of carbon monoxide poisoning. So back when we did hemoglobin and myoglobin, we talked a little bit about carbon monoxide poisoning versus just regular oxygen binding to the hemoglobins or myoglobins, and how your body has evolved to deter carbon monoxide poisoning because there's steric hindrance here. But both of them, O2 and CO, both bind to iron. CO binds really, really, really well, binds better. Binds better to heme. And again, the heme is part porphyrin, part iron. All right, so we've met several hemes. We've met all three types of hemes that you'll ever be introduced to in this class. We have B-type hemes that are associated with hydrophobic residues. So the hydrophobic residues of the protein would interact with these functional groups right here. C-type hemes are associated via disulfide bonds or by covalently linking to a cysteine. That's how it's attached to the protein. And then A-type hemes have these large isoprenoid groups, which are also associated via hydrophobics. Okay, remember the B-type hemes belong to complex 3, and C are complex 3, and then the mobile electron carrier cytochrome C. And A is complex 4, is where it's associated. And I wonder if you can remember which one of these types of hemes belongs to hemoglobin or myoglobin. And hopefully what you remember is that, or you can deduce, it wasn't covalently attached. The heme is not covalently attached to hemoglobin or myoglobin, so it can't be C. We haven't really talked much about this large isoprenoid group, so I would say it can't be A, so it's B. So hemoglobin and myoglobin have a B type of heme. But what I want you to see is that all of these have an iron right in the middle of them, which means that certain poisons will strongly attach. All right, so these are the poisons, cyanide, azide, and carbon monoxide, that will bind to any heme. And if it's electron transport chain, it will halt the flow of electrons, so that's not good. But chemical asphyxiation specifically occurs at complex 4. Okay, so here are the ions attached to the poisons. Cyanide's a poison, carbon monoxide's a poison, and azide is a poison. And the reason that chemical asphyxiation occurs at complex 4 is this is where O2 binds. Okay, so asphyxiation, you may normally think of asphyxiation as like a physical asphyxiation, someone being strangled or someone being smothered. Basically, oxygen is no longer going in and getting to where it needs to go. In chemical asphyxiation, the oxygen is blocked by a chemical. Okay, so these ligand molecules here compete with O2. And the reason they're competitive inhibitors is because they all kind of look like O2. Most of them have just 2 atoms. They're all linear, so they look like O2. They bind like O2, but they are not O2. And chemical asphyxiation doesn't occur at complex 3 because O2 doesn't bind at complex 3. But it will stop the flow of electrons if these do bind at complex 3. So it's not that they can't bind at complex 3 to like a type B heme. It's that O2 doesn't bind there, so it's not a chemical asphyxiation. It would still be detrimental to the flow of electrons and the generation of the electrochemical gradient. Okay, so last little thing, I don't know, this always feels just a teeny tiny bit out of place, but what about the NADH from glycolysis? The NADH those electrons do eventually get to complex 1. All right, so if you don't remember what I'm talking about, we're going to do this again. Don't know why I'm all into this yellow. Okay, glucose enters a cell. It is broken into 2 equal pieces, pyruvate. Pyruvate enters into the mitochondria. Partially broken down by the PDC, but from the PDC, this acetyl-CoA goes into the TCA cycle, and I'm going to go malate to OAA here, and then it just keeps going around and around and around. On the inner mitochondrial membrane is where the electron transport chain is. Okay. And all of the electron carriers that happen to be in here go to the electron transport chain. It's a little bit misleading. Actually, you know what I could do? I wonder what this is going to do to the video. I have no idea. Just roll with me for a second on this. Well, let me erase that too. Oh yeah, bye-bye. Okay, what if I did... Instead of making it misleading, this just might blow your mind. Okay. Okay, so I'm going to put my electron transport chain here. Complex 1 to complex 4. Now, I'm going to connect this TCA cycle here, because one of the reactions on the TCA cycle that enzyme is complex 2, the one where FAD comes from. And then I'm actually also going to put back in here malate to OAA, because that's going to be important for what we're going to talk about. So this one right here is where, just make it really big, FADH2 comes out and passes to a QH2. And so this enzyme right here is part of the TCA cycle. Okay, the other reduced electron carriers that come out, like NADH, have to find their way by diffusion to complex 1, for example, NADH. If you'll notice, this NADH is sort of analogous to lactate dehydrogenase. If you regenerate NAD plus, then you keep making the substrate that you need for the TCA cycle. And the only way to regenerate that NAD plus is to breathe. Okay? if you don't have oxygen, none of the electrons will flow through the electron transport chain, and you just won't be able to make NAD+. Okay. Let's see, what else did we get out of here? A GTP. And most important of all, CO2. Okay. I'm not going to draw the lipid oxidation one because it's just going to take up just way too much space. Okay. Get some ATP, NADH. Again, I got two of those. Fermentation is happening. Lactic acid regenerates NAD+, which goes back in here. Okay, so somehow I don't want to waste these electrons from NADH. I want to get them over to the electron transport chain so that we can create the proton motive force or the electrochemical gradient so we can make some ATP finally. And the way that this is done is using what's called the malate-aspartate shuttle. And I gotta zoom in here. So you have some aspartate, aspartic acid, an amino acid. And the first thing that happens to it is the nitrogen is removed from it and it becomes OAA. And the way the nitrogen is removed is an alpha-ketoglutarate, one of the intermediates in the TCA cycle, will steal the nitrogen off of it to create glutamate, GLU. So we create a different amino acid. Basically, the first step is pass the nitrogen, pass the NH2 to get to OAA. And then the next thing that happens is OAA is converted into malate. And the way that it's converted into malate is you add the electrons from NADH to make NAD+. So this is the reverse of what happens in the TCA cycle. This malate can cross into the matrix, and then it will rejoin up here to the TCA cycle, and if you'll remember, this is one of the reactions in the TCA cycle that spits back out an NADH, and then this NADH can enter into complex 2 as long as you're breathing. To complete the cycle, oxaloacetate can grab a nitrogen. Oh, I didn't really make that arrow long enough, did I? Let's make it a little bit bigger. I'll just zoom in here. This oxaloacetate can grab a nitrogen, guess from who? A glutamic acid to make alpha-ketoglutarate, and then this aspartic acid to complete the shuttle goes back into the cytosol. And then this alpha-ketoglutarate here can enter in sideways back into the TCA cycle. Okay, so what I want you to see, this is called the malate-aspartate shuttle. Because OAA or oxaloacetate never crosses the membrane. And what you'll also notice is that this NADH also never crosses the membrane. It's not piggybacked onto anything at all. It's just the electrons from here are moved to this malate, and once the malate gets back into the matrix, those electrons are moved onto an NAD+. So the only thing really from glycolysis, from the NADH that's moving, are the electrons. And the NADH itself does not cross the membrane. So if you were to C13 radio label this NADH, you would not find any C13 NADH in the matrix because those atoms don't cross the membrane. Okay. Oops, that was supposed to be erased. I don't know what just happened. What am I clicking on? Don't. Go away. The other thing that I want to point out about the malate-aspartate shuttle is that because of the transport process, the NADH from glycolysis is not worth as many ATPs. And that's because we lose some energy in the process of transporting. Just food for thought. Okay, so just one more time. Glycolysis creates NADH. In order to not waste those electrons, they can be shuttled across into the matrix. And the way this happens is through the malate-aspartate shuttle. So the first thing that happens is we have some aspartate in the cytosol. It gets deaminated, which means it just removes the nitrogen to create glutamic acid. We get oxaloacetate, which can be reduced to malate. Malate crosses into the matrix and rejoins the TCA cycle right where it's supposed to. Malate is oxidized to oxaloacetate and spits back out an NADH, or really just moves the electrons from itself onto an NAD+, creating NADH. Oxaloacetate can gain back the nitrogen, creating aspartic acid, which then again gets shuttled. Okay, that's the malate-aspartate shuttle. The last thing that we'll do before moving on to anabolic pathways is the ATP synthase, and that will be next time. All right, bye-bye.